Hello everybody, welcome back. We are moving right along through all of our endocrine organs. This video is going to be covering the adrenal gland and the pineal gland. So they're not really related to each other, but they're both relatively small, so I figured it would be okay to smush them into the same video. So let's take a look at the adrenal gland first. So anatomically, the adrenal gland sits on top of the kidneys. Depending on your resource, and they've gone back and forth, you might have it be called adrenal gland, you might have it be called suprarenal. Either one of those is fine. I learned adrenal, so that's kind of what I always fall back on. So the adrenal glands are just kind of small little triangular shaped glands sitting on top of the kidneys. There are two major regions. We have what's called a cortex, which is the outer layer, and we have the medulla, which is the middle. So hopefully you're getting comfortable with the idea of a medulla being the middle of something, because we're going to see that quite a bit more. It does have a capsule, as most solid organs in the abdominal pelvic cavity have a capsule to separate it from other organs and tissues. So your adrenal medulla, or let's talk about the adrenal cortex first. So it is divided into three zones. Let's see if I can highlight those. So we have, in this case, the medulla is in the middle, and the innermost layer is called the zona reticularis. The biggest of the cortex is called the zona vesiculata, and then the outermost layer is called the zona glomerulosa. So each of these layers or zones of the cortex produce a different set of hormones. And then the capsule is the connective tissue outside, and then the medulla produces epinephrine and norepinephrine from sympathetic activation. So we'll talk a little bit more about that next. So let's take a look at the three different layers of the cortex and see what hormones they produce. So the zona glomerulosa, which is the outermost one, it produces your mineralocorticoids. There we go. The main one is aldosterone. Okay. Mineralocorticoid is just a general term, but it might help you remember that aldosterone regulates sodium, because sodium is like a salt, it's kind of like a mineral. So aldosterone helps to regulate your sodium and potassium levels in your bloodstream. It is humorally stimulated because it's regulating blood levels of things. So it is monitoring, again, just like your calcitonin, PTH, your thyroid and your parathyroid gland. This zona glomerulosa is monitoring the blood levels for calcium and potassium and will be secreted if those levels are off and they need to be remedied. So the target for this, I'm going to try to draw the best I can. Targets the kidney tubules. So I'm going to draw a cross section of a kidney tubule. And right next to it is going to be a blood vessel. Okay. So in the presence of aldosterone, so if ADH, they'll say is kind of this orange hormone. So if ADH comes to the bloodstream and eventually lands on these cuboidal cells, what they do is they transport sodium from the filtrate, what is going to be urine, and put that into the bloodstream and kick out potassium. So it's almost like a sodium potassium pump triggered by the arrival of this adrenal aldosterone. Sorry, I was thinking ACTH, pituitary gland. So aldosterone comes in, binds to these cuboidal cells in the kidneys, triggers the release of, or the absorption of sodium and the kicking out of potassium. But what all of that sodium dumping into the bloodstream ultimately is going to do is water is going to follow salt into the blood. So not only does it regulate blood levels of sodium and potassium to keep those normal, it is also triggered by low blood volume and low blood pressure. So if you have that condition, aldosterone will be triggered to be released to help you absorb water. And you absorb water because water is going to follow the salt, the sodium that is also absorbed. So it's kind of like an indirect water reabsorption. Okay. So that is our aldosterone. In the zona vesiculata, we have corticoids. Okay. So corticoids, glucocorticoids, cortisone, cortisol, these guys target most of your body tissues. So we have receptors all over the place. Their job is what's called a glucose sparing effect. So it's usually a stressor is going to cause you to release these hormones. triggered by ACTH. This is a hormonal stimuli. So from the ACTH from the anterior lobe targets your zona fasciculata, triggering these cells to release glucocorticoids, released to the body, releases amino acids to be metabolized, can be converted into energy, releases fatty acids to be turned into energy, can release sugars from your liver or help you produce and store sugars, promotes liver formation of glucose and glycogen, promotes peripheral utilization of lipids. So that's its primary role, is to kind of release nutrients, if you will, to be utilized for energy reserves. A secondary effect of these is it's anti-inflammatory. So if you've ever, used hydrocortisone, it is a corticosteroid that has a topical anti-inflammatory effect. Sometimes people getting injections of cortisone shots that you may have heard those are anti-inflammatory. It's not the primary role, but it is a useful role for people whose tissues have excess inflammation from immune responses or trauma or things like that. Little side note connection is, you may have kind of made that connection already, corticosteroids are released naturally during stressful situations to kind of maintain your energy and your metabolism. So if you're in stressful situations a lot, releasing a lot of these corticosteroids, you're also doing a generalized reduction in inflammation, which is a big part of your natural immune response. So you become immune compromised when you have high levels of these corticosteroids circulating through your system. So just be careful and be aware of that. The zona reticularis, these produce androgens, which are like testosterone, sex hormones. The function of these is not really known. And I'm not going to talk about the function of testosterone here just because we're going to talk about it again when we get to the testes in our other tissues, as well as when we get to the reproductive system at the end of 233. So there really is not much known about the androgens that come from the adrenal cortex. They do target most cells. Your book says prepubescent pubic hair stimulated by adrenal corticotropic hormone. But it's so small, it's not a huge impact on most day-to-day activities. So we're not going to spend too much time on it. All right, so those are your adrenal cortex hormones. So aldosterone, corticosteroids, and androgens. So the last part are your epinephrine and norepinephrine from the adrenal medulla. Now, we should be pretty well versed on these functions because we did a whole chapter, half of a chapter on this with sympathetic activation. So you should know that epinephrine and norepinephrine come from the adrenal medulla, neurally stimulated by those sympathetic preganglionic neurons, targets almost all cells, triggers sympathetic activation like increased heart rate, increased respiratory rate, decreased urinary and digestive functions, mental acuity, increased skeletal muscles becoming more tense and ready to fight or flight or freeze or exercise, right? So a little bit of review of sympathetic activation there. All right, so that's our adrenal gland. Next, we have the little pineal gland that sits in the back of the diencephalon. We kind of associate it with the epithalamus. So the pineal gland releases one hormone called melatonin. Some of you actually may take it as a supplement. It does help to start your sleepy time, that cycle from your circadian rhythms from consciousness to unconsciousness. It is an interesting one because it doesn't really fit into that stimuli. I would say because your book doesn't really describe it. I think I've described melatonin before as being neurally stimulated because it is triggered by the decrease in light stimuli. So the sun goes down, you turn the lights off in your house, your eyes close. So those are neural stimuli coming from your visual optic radiation, right? Coming back from your eyeballs back to your different parts of your brain. And so as that neural stimuli decreases, that's what increases the pineal gland to produce melatonin. So I'm just going to say neurally stimulated. And it targets part of the brain that regulates your day-night cycle. So it probably goes and targets reticular formation, maybe your cerebral cortex, various places in your brain. I did find this kind of cool graph here that shows the levels of melatonin and how they're highest in the younger individuals and how they decline over age. So this is about 10 p.m. to 6 a.m. So this is 10 p.m., right? I think that's military time. Yeah, because 2400 is 12 midnight. So from 10 p.m., this is kind of the dark time. This is your body is shifting from that conscious state to the unconscious state. And so that's when your melatonin levels are going to be the highest. Okay. All right. It also has some antioxidant functions, which is kind of cool. So they break down free radicals. And then lastly, it also inhibits reproductive functions. So also you can see it's highest here in those prepubescent years. And as it gets lower, it stops its inhibition, which helps to start the changes of the body in puberty, plus a whole bunch of other things. I'm not going to say puberty is completely driven by melatonin in the pineal gland, but it does play a part in that transition from childhood to adulthood. All right, so that is our adrenal gland and our pineal gland. Next, we are going to talk about the pancreas. I will see you then. Bye.